Okay. Hello, everyone. Welcome to the MIA Academy, the seventh session about anaerobic digestion modeling. The session of today will again be recorded and available on YouTube afterwards. So today, Damien, Batstone, and Ismail will present on anaerobic digestion. Damien, you want to start by introducing yourself? Then you can introduce, and then we can start the session, I think.
Yeah, thanks, Liz. Yeah, Damien Batstone. So I developed the ADM1 together with a heap of other people about 25 years ago. And we've then applied it across many different places, including within MIA in the benchmark simulation model number 2. So we've also had input to development of a couple of other models. Those being used particularly in commercial simulators like Sumo and BioWin, mainly just providing some input there, not as developers at all, but also had because of the complexity of the chemistry in anaerobic digestion, had a fairly big impact on development of complex chemistry models in wastewater treatment as well. And I'm coming from Brisbane, Australia, where it's 10 p.m. at the moment. So great to meet you all.
Hello, everyone. I'm Ismail, PhD candidate at Toronto Metropolitan University and Ghent University. I'm based in Canada right now. My research is on greenhouse gas quantification and modeling from wastewater treatment plants and sewer networks. And my anaerobic digestion credentials is that I did my master's in anaerobic digestion, so I know one thing or two about it.
Okay, thank you. So Damien, if you want, you can start to share your slides and start this session.
I'll do that. I've just got to get the share screen back again. Okay, so I guess I'll actually dive into the ADM1. So it's a standardized model that's basically used as the basis for many other digestion models. It was actually developed out of about 6 or 7 different models that people have been working on across Denmark, Switzerland, the USA. Spiros Pavlostasis was a contributor. Everybody had different models, but they were all used for different things. So Irini Angulodakis was used for olive oil and manure. Spiros's was for sewage sludge. Mine was for industrial wastewater. So we came together and we focused on kind of putting together an aggregate model as well as a roadmap for how to do digestion modeling. And there's a couple of tricky things in digester modeling that don't exist in other treatment plant modeling. As I said, the chemistry is very important. So we published in 2002 and we presented AD9 in Antwerp. And it was really quite interesting because we got a lot of interest from not just modelers, but also people who are doing microbial ecology. Lut Raskin was there and asked about the model. And it took a clade-based approach, which is the approach that everybody else has taken. But it wasn't particularly new. So it was really an aggregation of previous approaches. It's actually accelerated in uptake. So about 10 years ago, there were still quite a few different models being used, but now you go to conferences and often it's the basis for people to build other models. So you see more and more that people are producing standardized, simplified, or taking the ADM1 and adding, for example, acetate oxidation or something else. The print run's actually sold out. It should be open access. I'm not sure. I think it is in some places or not in others, but it should be one of those which is now open access, and I've got to actually check that. But it's cited in something like 60% of AD modeling papers, and more recently, probably even more. So it is a generally used model. And this is what the original structure was like. So we did one thing in the model which was original, not in other models, and that was we had this 2-step disintegration and hydrolysis process, and that was actually a mistake. We shouldn't have done that. We should have just had, and in fact, now our entry points tend to be around here. So if we've got a mainly soluble substrate, we'll take our entry point in the solubles. If we've got a mainly particulate substrate, we'll take our entry point in the particulates. There's other approaches. So the other approach is to make your entry point uniformly particulates, but then if you've got a soluble substrate, is to make this rapidly degradable. There's no wrong answer, but we never use XC, the complex particulate material, as the entry point anymore, because essentially it makes this a two-step process, whereas it should really just be a single-step hydrolysis process. But we've got basically 7 microbial clades. So we've got 3 fermenter clades, or really LCFAs are oxidizer clade, but 3 clades that take up the primary substrates. 2 acetogenic clades for propionate and the mixed clade for valerate and butyrate, and that was based on evidence that indicated that C4 and C5 fatty acids were both converted by the same organisms. Acetoclastic clade and a hydrogen utilizing clade. And basically there are other potential clades, and I'll talk about some of them a little bit later, but this captures probably 90% of standard anaerobic digesters, not just municipal digesters, but also manure digesters and plug flow digesters and industrial digesters. Things like acetate oxidation start to dominate when you have very high ammonia concentrations or very high temperatures. So ammonia oxidation is where you get acetate going to hydrogen and then hydrogen going to methane. So that's acetate oxidation. But really this standard process where we've got a mainly acetoclastic clade covers most digesters. You can also get things like other substrates. You can get ethanol or lactate. Monosaccharides can actually divert via lactate as well. But as I said, most of the time, the standard structure works for most cases. And really, there's a balance between hydrolysis, which determines your performance, and the bottom end, particularly acetoclastic methanogenesis, which determines your stability. So it was a bit focused on municipal, but it's very broadly capable. So it works for a number of different digesters, and I'll talk about some of the applications in a minute. And there's a lot of different versions out there. Aquasim, MATLAB, Python, C, and version creep is actually a bit of an issue. So one of the complaints I get a bit is I don't know which version to use, and that's a valid complaint. We've also got the 2 inert ones, and Amir will talk a little bit more about that as well. They're very similar to inerts in activated sludge modeling. Okay, so there's a couple of tricks with digester modeling in general. So you'll know, I'm just going to move this bar out of the way. Yep. So you've got pretty standard mass balances, dilute assumption in general in your soluble phase and your gas phase. So you've got your soluble components where you've got your standard mass balance equation with dilution and conversion. The difference with activated sludge and aerobic digestion in general is that you need a gas phase. So that gas phase is basically, it's a normally fixed volume. It can be variable volume. That's actually not really a problem either. So you can have an anaerobic sequencing batch reactor where your liquid phase is increasing, your gas phase is decreasing. That can be done, but under the standard implementation, you've got a fixed volume for your liquid phase and a fixed volume for your gas phase. And that's a little bit tricky because you've got gas liquid transfer between the liquid phase and the gas phase. That can be bidirectional. So you can have gas going into liquid and liquid going into gas. And normally it will be from liquid to gas. So we'll have methane, CO2, and hydrogen transferring from the liquid to the gas phase. But some of the newer applications, for example, biomethanation, where we're injecting hydrogen into the gas phase, which then transfers to the liquid phase to make additional methane, that works perfectly well. We've still got the same equation, KLA times C sat minus C, and it just works. The tricky bit is that the gas flow rate needs to be set. And there's a couple of approaches to this. One approach is to basically set the net flow rate to the net transfer rate. So you've got transfer of gas, hydrogen, CO2, and methane, and you set the net flow rate to the net mass transfer rate. That's how most people did it until the ADM1. But then when we did the ADM1, for various reasons, including flexibility for things like sequencing battery reactor and variable volume gas phases, we decided to do it using flow through an orifice kind of equation, where we've got the pressure differential between the gas phase and the atmosphere then drives the flow through an orifice parameter. You might know that flow through an orifice should be a square root of this equation, but it doesn't really matter because we just want K big enough that we don't actually end up with a big difference between the P and the P atmosphere. And one of the mistakes we see new users do is to treat this as a fittable parameter. It's not. It's just there to make the gas flow basically minimize the pressure drop between the pressure in the headspace and the pressure in the atmosphere. So you don't treat that as a parameter. You just set it as a big number. If it's too big, you end up with a stiff set of differential algebraic equations. So you try not to make it massively big, but it needs to be big enough that you don't really get substantial pressure fluctuations in the gas phase. The nice thing is, industrially, that's turned out to be quite useful because it does simulate actual gas headspace behavior in things like compressible headspace digesters or even floating roof tanks. So it makes it able to simulate the actual system quite well. So it's been used for a very large range of digesters. These are all the types of digesters that we have simulated or people have simulated using the ADM1. So you've got, this just shows digester types. You've got hydraulic retention time on the y-axis and feed solids concentration on the x-axis. So this just defines where different digesters will operate. So high rate anaerobic digesters treat mainly soluble feeds. They can be quite high strength, but the feed will mainly consist of sugars, soluble proteins, and maybe some soluble fats. So think things like brewery wastewater, beverage wastewater, ice cream manufacturing, something that is very low in solids but quite high strength. So you've got this granular sludge that forms. Under this regime, you've got a very rapidly degradable feed that will produce VFAs very quickly if you let it. And you're really challenging your process stability rather than the process performance. So it hydrolyzes it, well, the hydrolysis doesn't even really happen. It often ferments before it even hits the digester. Then you've got anaerobic membrane bioreactors. So that's simulated similar to aerobic MBRs, except we've got gas being recirced instead of aerobic scouring on the reactor. Anaerobic lagoons, just very long retention times with solids retention. Sludge digesters, where we've got the main problem, because we've got a completely mixed reactor, the main problem is the input characterization, trying to work out a conversion extent. And as we get to higher concentration, things like inhibition, particularly ammonia inhibition, becomes a problem. We might need a pre-treatment model to discuss how thermal hydrolysis might affect us, or we might have acid gas pre-treatment. I'll talk about some of the pre-treatment models as I get through the rest of the session. Plug flow, where we've got very high solids in the feed, and it's basically going through as a plug flow through the digester at 10% plus solids. And in this case, we start to get process stability issues, because if you get a failure in the front, that failure then propagates down through the digester. We have to simulate the concentration profile through the digester as well. And the model can simulate all that. It can simulate that stability issue that you get with plug flow digesters. And then we end up at the very high solids concentration with basically solid phase leach bed. That's where we've got a liquid flow through a leach bed, the liquid then being digested in a high rate anaerobic digester, and then the liquid flowing back through the leach bed. So that normally requires a 1 or 2D or even 3D model implementation. So there's modeling approaches to all of these, but of course we're mainly working with our municipal liquid phase digesters. So we're working in this region here, which may include pre-treatment. Okay. So there's been a few key changes over the years, and particularly in the last 5 years. And this has been, particularly in the last 5 years, it's been driven by municipal applications. So the changing needs in the digester space, as well as the changing modelling needs, as well as the change in technologies that have been applied to digester modelling. The big change has been in plant-wide modelling, and Amir will talk a bit about this a bit more as well. But plant-wide modelling was a big change because one of the things we really needed to do was to model P throughout the whole process, and that allowed things like nutrient recovery, implementation of technologies such as struvite and more recently vivianite to recover P. But to model P plant-wide, you need to also model iron and sulfur. To model iron and sulfur, you need a very good chemistry model, and that then led to the PCM1. And in parallel, PCM1 didn't precursor this, but in parallel, there were some big updates to Sumo and BioWin to incorporate sulfur, phosphorus, iron chemistry, and the advanced iron chemistry needed to really model precipitation and a few other things. So this led to development of advanced chemistry models, which include a lot of non-ideal stuff like iron activity, iron pairing, its downstream impacts on gas-liquid transfer, full incorporation of temperature into that chemistry model, and a few other things. But that's a big extension of the model because you don't just have the chemistry extensions, you've also got all these biological extensions needed to essentially describe sulfur oxidation reduction, iron oxidation reduction, as well as phosphorus release and uptake, both chemically and biologically. Just checking the thing. Yep. Okay, the other big change over the last 5 years has been emerging technologies. So until recently, the only real pre-treatment that had substantial success was thermal hydrolysis, and that's where you basically cook the sludge. And that was quite easy to model because we just made it more degradable. We didn't really have to model the viscosity effects, and we increased the inert fraction because we know that thermal hydrolysis produces some colored compounds which are non-degradable. But there's been a heap of other changes emerging over the last 5 years, like recoup thickening, microbial hydrolysis processes, which is basically a cyclic thermophilic mesophilic process, vacuum intensification, biomethanation. Now, it turns out that these are process changes that the model is largely capable of dealing with. So these don't actually change the fundamental biology of the process. And the existing biochemical structure actually deals with these processes quite well. So we can model biomethanation by just adding hydrogen. It works really well in the stock ADM1. We have to increase the KLa to model it effectively, but it actually works very well. We can model, if we've got a thermophilic step and we've got a recirculation, we can model some of the stuff that happens with microbial hydrolysis processes because it goes through a mesophilic process, then it goes through thermophilic that releases material. It converts hydrogen to methane. It also deactivates some of your acetoplastic methanogens and results in that becoming available. So we can actually model, and recoup thickening is really easy because we just return the solids back into the digester. So it actually models that quite well. MHP's definitely got acetate oxidation as an additional process, but apart from that, it's not that different from what we already model. So the ADM1 and Sumo and BioWin models are not that different, particularly for municipal sludges, which they've been designed for. They're actually quite capable of novel processes because the biology is not changing that much. But particularly this iron, sulfur, etc., that resulted in some pretty big changes. So we've got sulfate reducing to sulfide, which then can, under aerobic conditions, can oxidize back to elemental sulfur. We can actually engineer that to remove sulfide in the anaerobic digester by adding a small amount of air to oxidize it to sulfur, and that's quite easy to simulate as well. We can get iron basically reducing or oxidizing. We can get other metals like manganese also reducing or oxidizing. They're quite easy to include. Of course, iron will tend to precipitate differently as Fe2 versus Fe3. So it's very important when you go into a digester, you reduce your iron from Fe3 to Fe2. That then releases the phosphate, binds the iron with sulfide, because Fe2 will bind with sulfide to form iron sulfide. It can also bind differentially with phosphate to produce vivianite. So this swing of iron then drives solubilization precipitation in a really interesting way, but of course a way we should have to model as well. We can get alternative substrates like lactic and ethanol, which I've already talked about. They're very easy to incorporate. And as I said, we basically eliminate this step here. We don't do disintegration anymore. We just treat the primary substrates as primary substrates, and the only thing we use disintegration for is a pool for biomass decay to go through, and even that is not really necessary, but it's kind of convenient. So our primary substrate entry points now are here and here, and mostly for sludge, which Amir will talk about, we go into this point here, and that was a result of particularly the no-pens interface when we put together the BSM2. Just showing you how it fits into a plant-wide context now. We can see we've got iron basically reducing in the primary clarifier. Sulfate will reduce as well. It'll probably already be reduced from the sewer. We've then got phosphate forming metal phosphates, iron being oxidized. That should be Fe3. Sulfide being oxidized to sulfate. And if you've got a lower DO sulfur, elemental sulfur, phosphate forming, not really iron phosphate, but Fe hydroxyphosphate. So you'll form these iron hydroxyphosphate flocks. So this process here has become a little bit more complex, mainly driven by Elen-Aduk, which we've incorporated in the PCM1 as well. You'll then go into your digester. Your iron phosphates will, because your iron will reduce again, it will release the phosphate. You'll also end up with poly P releasing, hydrolyzing over a longer time period. So that's actually a kinetic process. We've got iron reducing, sulfate reducing, sulfide binding with iron, phosphate forming calcium phosphate, and potentially iron phosphate if you've got a heap of iron around. And then you can do stuff like struvite precipitation or capture in the return stream to then try and recover phosphate. So inclusion of all these processes and inclusion as well in the activated sludge modeling bit of these additional processes is kind of essential to model P, which is essential to basically have a competent plant-wide model. So this is just showing this in a bit more detail. I'll probably skip over this because I am getting a little bit shorter on time and I want to show you some other stuff. Okay, so this is the other area which has been difficult to communicate. I haven't ever published it, but I have talked about it a lot. And this is how practically I treat inputs now. As I said, I don't use the XC. Forget about that. I basically take everything and I separate WAS and primary into two different streams. And these then, I'm actually going to use my pointer. These get separated in two streams, and each of these streams then gets split into carbohydrates, proteins, lipids, and inerts. So these are our four main components in any particulate stream. So they get separated into those four main components. Now, the protein content is set by the nitrogen content in the stream. And as I said, we've got one of these for WAS and one for primary. So the protein content gets set based on the overall nitrogen content, and the carbohydrate lipid ratio then gets set based on the energy density, the CODVS fraction, and then the inert component just gets set based on degradability, which I call FD. So it's FD for primary and FD for WAS. So I've got two degradability parameters. So it's a bit complicated, but it ends up being quite nice because my nitrogen content is set by the proteins. My energy density is set by my lipid carb ratio. So I've got WAS, which has got a moderate energy density, primary, which has got a high energy density. Something like pure carbohydrates would have a a COD/VS ratio of 1. Something like pure fog, fats, oil, and grease would have a COD ratio of about 2.3 and would be almost all lipids, no non-degradable. So these relative fractions to each other, they don't change. That's your degradable fraction. This fraction is then a fittable parameter. So then I estimate these 3 parameters. Normally I'll lump the hydrolysis across everything. So I use the same hydrolysis coefficient for all of these 3 degradable components, and that's my single hydrolysis coefficient. But then I have 2 degradable parameters. One is the degradability of primary, and the other is degradability of WAS. And then I fit those 3 parameters simultaneously based on either gas flow and or outlet solids. And you can see here is a fit confidence region. And you can see that my degradability in my primary sludge is around 90%. My degradability in my WAS is around 12%. So this is a bit of an extreme example, but I've got very degradable primary, very undegradable WAS. So that's quite normal when you've got a primary settler and a very, very long sludge age in a tropical environment. Your WAS ends up being very undegradable. Your primary ends up being quite degradable. So this is a bit extreme, but normally it would be about, activated sludge would be about 30% degradable. Primary would be about 80% or 70% degradable. But you can see that I'm fitting all these simultaneously based on parameter estimation. And the nice thing as well is I can then track my WAS and primary units separately to get ongoing performance in both. And that's something you can't do without modeling. So I model a lot of full-scale digesters using this approach, and it allows me to basically say, okay, you're doing quite well on WAS, or you're doing quite badly on WAS. Your WAS is undegradable muck, or it's actually quite good. And that gives a bit of information, because the assumption's always been often that you're performing about the same on WAS and primary sludge. You could vary that parameter, but I find that these are the maximum number of parameters you can actually estimate. So that's my practical approach based on modeling quite a lot of digesters now. So this will be based on data like this is VSD. In this case, the model is the line, the data are the dots. So I'm working with quite a long time period, 3 years here. And you can see that a single parameter set is actually describing that whole 3 years. So you're not getting digested drift. And one of the things that we often see is we get a change in the sludge properties will result in digested drift, or a decrease in gas flow will be because you're starting to leak gas, for example, not because your inherent material properties are changing. Okay. So the other last thing I just wanted to talk about is version creep. So we've been around for 25 odd years, so there's been a bit of version creep. Now, the most definitive versions are probably the MATLAB and or C version. So we've got a MATLAB C core model, if you like, a model that hasn't been messed with, and then we've got the MATLAB C version with the iron, phosphorus, sulfur extensions and PCM1. So that's all available on Javi's GitHub. There's a few Python versions, mostly very much stock. So they've just been made a stock version. The most commonly used one is probably PyADM1, which is also on GitHub. And also there's a preprint article as well provided. The first version was actually Aquasim, but the Aquasim reference version still uses XC as a primary feed. There's all the versions that I've provided with my publications, also on GitHub. I don't have a GitHub site, but generally I'll publish a version with each GitHub site. But yeah, version creep and differences are a problem. And maybe that's something we have to do, is to just produce a definitive current version with the proper feed characterization and maybe a couple of reference examples. So that's a project for when I get a bit of time. So finally, to finish off, most people who are in MIA, I'm guessing, want this part of a plant-wide model, or want to model digesters. So sludge digesters, not all the other types of digesters I talked about. The BSM2 versions are generally consistent, both the complex version with iron, phosphorus, sulfur, and the non-complex version for simple digester modeling. I use the basic version for digester modeling unless you're trying to do plant-wide modeling. It's easier to interpret, a lot faster to use, etc. Sumo and BioWin implementations within the sludge world are broadly compatible with the BSM2 ADM1 with or without physicochemical extensions. Both Sumo and BioWin allow you to turn off the physicochemical extensions. And just last thing is recall domain specialist knowledge. So people get confused about pH balancing, performance versus stability. So think about what's actually happening. And a common issue is not understanding this ion chemistry issue. So having your pH decrease massively because you forgot to put in cations, for example, and that just makes the biological process fail. So one of the things we often recommend is turn pH inhibition off or on to basically test out the model. With that, I think I'm out of time anyway, and I think we got questions at the end. So I'll turn it over to Amir and stop sharing.
Thank you, Damien. I'll start sharing my screen now. Can everyone see this? Okay. So I'll be talking about anaerobic digestion within plant-wide models. First thing is basically the notation, moving from ADM1 to ASM. So for your composite particulate material, that's basically your total COD. That's your sludge feed to the digester. This integration here, it goes from carbohydrates, proteins, and lipids and inerts into acidic fractionation, which is XS, which is I think is the equivalent of XC basically. So XS is the particulate biodegradable substrate. XB is your biomass that goes into the digester, and XI are the inerts that are in the feed. And there before in earlier versions of ASM, there was no distinction between influent inerts and inerts that are produced throughout the biological process, as in accumulation of decay products. They were both considered inert material, but now they have a distinction between XI, which is influent non-biodegradable material, and XE, which is endogenous products. And then hydrolysis here is basically everything hydrolyzing, which is only the biodegradable fraction being hydrolyzed, which becomes SS in some model notations, or SF as in the fermentable substrate in the notation of ASM1, and I think the rest of the ASM, the other ASMs. And then here, there's no differentiation between, in ASM notation, there's no differentiation between acetogenesis and acetogenesis. It's just combined into one process, which is fermentation. And this is where you start producing your VFAs and hydrogen. And in some models like BioWin, they have a differentiation between they don't just lump VFAs, they have propionate and acetate and also hydrogen production. And then your final process is basically producing methane, and it's just soluble here because you produce it as a dissolved gas, and then it gets stripped into the headspace. And this is what you end up with. You end up with a model that you have basically your total CD that goes to the digester is here. This integration is just basically fractionation. So you have Si, which is the soluble non-biodegradable material. You have very little of that in your sludge feed, but since the model considers everything as completely mixed, you end up with some of it in the digester. You also have the Xi, which is the inert non-biodegradable. It's just non-biodegradable CAD, but that's the one that comes in the influent. And XB is basically just your biomass, and you also have some of the biodegradable particulate material that it's enmeshed into your biological flock. And with anaerobic decay, your biomass, which is probably, if you look at the decay models, they have the the death regeneration model. So whatever is intracellular material in your biomass, it becomes XS, and then you also have XE, which is your endogenous decay products. So this is about anywhere from 15 to 20% of your biomass, and then the other fraction is just biodegradable material that will be utilized later in this cycle. And then with hydrolysis, you end up with SF, which is a fermentable substrate, and then fermentation, you have VFAs, hydrogen, and also carbon dioxide being produced, and then you end up with methanogenesis. The difference here between the explicit difference between ADM1 and ASMs is that we don't have the lipid, carbohydrate, and protein degraders. It's all carried out by ordinary heterotrophic organisms, which is not true, but it is how the model is structured. So the one thing that we need to look at when we're looking at digesters is that they're not a separate entity. They are part of the wastewater treatment plant, and anything that happens upstream dictates the performance of your digester. So your influent fractionation characteristics, that dictates the amount of non-biodegradable material that we will end up with in the sludge, which never changes. Physical separation efficiency, your grit removal efficiency also impacts any downstream process and your digester, and also primary and secondary clarification. Also, the operational SRT impacts the digester's performance very much. Because all of these combined dictate the quality of your primary and waste activated sludge, aka your digester's feed. So when we look at the influent fractionation and characteristics, this is basically a map from SOMO showing the influent tool. This is your total COD, and it's basically you fractionate it into a soluble and particulate fraction, and each one of those is broken down into different fractions. And this is where your disintegration step comes in, basically. So what happens is that you have this fraction, which is XU, which is a non-biodegradable particulate COD that comes in the influent, and it's about 14% by default. It changes depending on your plant, but basically by default in SOMO it's around 14%. And you also have the XE, which is around 1%, which is the endogenous products coming in the influent, because there's biological processes happening in the sewer, and you end up with a fraction of endogenous products also. But these fractions change as you go from the influent all the way to the digester, not because there's accumulation with this fraction, but because you change the other fractions, and then as a total percentage, you end up with a different percentage of these fractions. So XB, which is your not biomass in this case, in SOMO notation, that's basically your biodegradable particulates. All of this is going to be consumed anyway to produce more biomass. And then you have your VFAs that are also going to be consumed to produce biomass. Same thing with the biodegradable soluble substrate, and same thing with the colloidal substrate. So when these fractions are utilized, they end up producing more bacteria, which is your active biomass, which is XOHO, and you also, with decay, you end up accumulating XE. So you end up with around this fraction from 14% goes up all the way, could be all the way to 40%, depending on how your operation is. So the first thing that I call a biodegradability or a methane potential cap is XI. So you cannot, if your sludge has a 20% biodegradable fraction, you cannot go beyond 80% biodegradability, basically. So that's your first limit when it comes to methane potential in your digester. Second thing is primary clarification and secondary clarification. So primary clarifiers intercept COD before the aerobic tags. So it captures all the solids, the good quality solids that can go into the digester before being oxidized and synthesized into biomass. The more you capture in the primary clarifier, the more methane potential is preserved, and it's basically the highest quality feedstock in the plant. Secondary clarification recovers COD, but after the aerobic tag. So instead of the good quality primary sludge, you end up having more biomass as waste activated sludge being captured in your clarifier. And also you have endogenous residue that has been already respired, which is throughout COD aerobically. So it recovers basically what survives, but in a reduced methane potential form. Because waste activated sludge is not as biodegradable as primary sludge because it's mostly biomass, so it's very hard to degrade. Also, grit removal has an impact on your digester because any grit that escapes could occupy active volume, and then you end up having short circuits, and your SRT, your operational SRT decreases because you're occupying that space. So grit removal ensures healthy operation, although it's not modeled explicitly, but something that you want to consider when you're dealing with a plant-wide model. The third thing is the SRT. So SRT is the most operational, most important design parameter, so to meet the effluent requirements. But as you increase SRT, the active fraction of biomass decreases. So the more SRT you have, the more decay you have, and then you end up with, as you can see, endogenous products. as a fraction of the particulate CD that I have in your mixed liquor. It starts at a 5-day SRT around close to something like 12%, and then you end up having almost 60% of your particulate CD as endogenous products. So you're doing two things here. You're accumulating endogenous products, and you're reducing the active fraction of the biomass, which is most of your methane potential. So your second biodegradability or methane potential cap is XE. But there's a caveat with XE specifically, which is, so are they actually inert? They are not. So endogenous products have been considered inert or non-biodegradable in most of the ASM notations before, and even with experimental studies, sometimes they have considered them non-biodegradable. But these models specifically were designed to model systems operating at SRTs no longer than 30 days. And with the introduction of membrane technologies and SRTs going all the way up to 400 days, they saw discrepancies in sludge production, which is the most important parameter you need to calibrate on when you're using any plant-wide model. So when they saw the discrepancies, that they were always overestimating sludge production, which indicated there was a process that was missing. And that process was basically the degradation of endogenous products at longer SRTs. So if you look at this table and this curve over here, these are the studies that have done work on the biodegradability of endogenous products. And some of them, you see that the rates are very slow, although they are faster aerobically than anaerobically. But there is a certain degradation to them. And that is not triggered unless your SRT is higher than 30 days when starvation conditions occur and your bacteria start producing lytic enzymes to degrade them. So why is this important? Because if your upstream process, you have a technology that operates at a higher SRT, you see that from this curve that after 30 days, at 60 days, you actually start accumulating less endogenous products because they're also degrading. So this is one thing that you need to consider, the fraction of endogenous products that's going to end up in your digester, which is something that you might even want to adjust in your bioreactors upstream to make sure that your sludge predictions are correct. The thing is here that, so it's kind of a summary. You look at XI and XE are the two caps on methane potential in conventional anaerobic digestion, because if your digester is operating at a longer SRT, you might see degradation of endogenous products in the digester also. The one thing is that reporting SRT is not a common practice in any in general. So you would, especially in anaerobic digestion, you would not see any information about the upstream processes, especially at SRT. Although understanding upstream operation and influent characterization and fractionation is integral to making accurate predictions. You can actually just figure it out on your own just by knowing the SRT. So just if you look at the non-biodegradable fraction over here in this summary, you'll see that it ranges a lot. Sometimes it's in the primary sludge alone, sometimes it's in the wastewater, and also the WAS. But you can, I just want to point out these three specifically. You can already guess that the non-biodegradable fraction over here is going to be high just because the SRT upstream is high. So you have 10 days aerobic SRT and anaerobic SRT of 60 days. And you can already figure out that it's going to be that high just by looking at these numbers. Although unbiodegradable fraction here doesn't distinguish between the ones in the influent and XE, but it's something that you can just guess by knowing the SRT of the system. So when it comes to good modeling practice of anaerobic digesters, AD mass balances are one of the easiest to close because you just have a sludge feed and your biosolids coming out, and then the gas that's coming out also. So the mass coming in is just your flow multiplied by the total CD concentration. Same thing with your biosolids, flow multiplied by effluent COD, and then the gas coming out is basically the difference between those multiplied by the stoichiometric conversion, which is at, so theoretical methane yield is 0.35 at STP, and you just do the temperature conversion, and that's basically your mass balance over here. But typically digesters covers do leak, and so the mass balance might not always close, but closure up to 80% is acceptable. I'm quoting Damien here from a meeting that we had 7 years ago. I don't remember. I don't know if this has changed, but basically closure below that might require some further investigation. So it could be a flow meter drift most of the time it is, pipeline modifications, operational disturbances, but you need to check this before you actually start the modeling exercise. Second thing here is hydrolysis. There's a distinction between ASM and ADM1 here because hydrolysis basically dictates the amount of volatile solids reduction or CD removal. Hydrolysis in ADM1 is first order, but hydrolysis in ASMs is surface limited, which is described by a Comtois model, and also modulated by redox switches like the Monod equation. So what these are the three hydrolysis equations in ADM1. So you have the hydrolysis of carbohydrates, proteins, and lipids, and each of one of those is just a first order equation multiplied by hydrolysis factor. But in ASMs, it looks like this. So you have the hydrolysis rate here, but it's also dependent on the amount of ordinary heterotrophic organisms you have in the system. And this is the Comtois term. So it's based on XB, which is basically your biodegradable particulate substrate, and it's dependent on OHOs over here. And this is your half saturation hydrolysis constant. And then the F redox here expands into this. So if you have an aerobic environment, this is the term that dictates what's happening. So it's just a Monod term. Anoxic environments, you have these kind of switches. So if nitrite is the electron acceptor, this term works. And then if it's this inhibition function is what limits it when it comes to nitrate. So nitrite existent, nitrate doesn't work, and the opposite. And all of this is also multiplied by a limiting function when it comes to oxygen, because if you have oxygen, you don't have an anoxic environment anymore. Same thing with anaerobic environments, but it's all just the limiting factors because there's no explicit electron acceptor here. It's mostly fermentative reactions where the electron donor is the electron acceptor. So once you have any of these, the whole environment is not anaerobic anymore. And that's basically what it would look like in your model. So you have rate of hydrolysis of slowly biodegradable substrate, rate of hydrolysis of substrate from biomass decay. So this is the differentiation between the biodegradable substrate that comes in the influent and whatever is produced from intracellular material. That's the distinction between those two. And then you have your reduction factor of anoxic hydrolysis, which is this term over here, and reduction factor of anaerobic hydrolysis, which is over here. So hydrolysis is slower in anoxic and anaerobic environments typically, and it's the fastest in any aerobic environment, and it's reflected here in the model. There's no limiting function over here. It's just the Monod equation. And also on the topic of hydrolysis, you'll see that hydrolysis rate in ASMs need to be adjusted basically to accommodate upstream operations. So low SRTs, you have more biomass, and then with that biomass being providing more biodegradability basically. So you end up with less endogenous products, more active biomass. So your hydrolysis rate might not need to be that high. High SRTs and lack of active biomass, then you might need to readjust your hydrolysis rate to accommodate for that. Because as you can see, if this term over here, you have less XOHO, so this term collapses and you need to compensate by increasing Q hydrolysis basically. Primary sludge almost has negligible biomass. So if you're doing fermentation, you might need to increase the hydrolysis rate to accommodate for the lack of biomass in that term. Hydrolysis rates in ADM1 models like BSM2 need to be reduced to accommodate for the loss of biomass coupling. But the rate is fit substrate only, so you don't need to scale it. But the one thing here that I want to point out is you can see that over here, you can see that the hydrolysis rate is 106 over here and 2.7 over here, but this is also for soluble substrates, as Damien mentioned before, that the model used to consider that it starts at a particulate substrate with the disintegration step, and then you start producing your soluble components. So for lactose, it's a soluble substrate, so you need to increase the hydrolysis rate just to accommodate that, because you're not starting at a particulate material here. You're starting with something that is completely soluble. So this is overcompensation basically. Also primary sludge, this is an extreme value, but it's the maximum value anyway. You'll see that most of the processes here have hydrolysis rates that are below 1. In any ASM process, you'll probably have to increase it beyond 1. Second thing is when it comes to fermentation. So we want to stop the process at this point over here. We don't want to produce methane. So during fermentation, you have both VFAs and hydrogen production. Operational conditions and feedstocks favor one product over the other. Carbohydrates produce more hydrogen, and you'll have to adjust your stoichiometry accordingly. But methanogenesis is either suppressed through washout or pH inhibition or both. So how do we stop methane from being produced? You can actually just go and just turn off their growth rate, but that's not how you model something that's just curve fitting at that point. So the caveat here is that acidoclastic methanogenesis has a shallow redox gradient and yields little energy per unit substrate. So that's why the growth rate is very low. So you can see that they have a growth rate of 0.3 compared to hydrogen-trophic methanogens, it's around 1.3. So acidoclastic methanogens can be easily washed out. So if your SRT is fairly low, like 3 days, the minimum SRT for acidoclastic methanogens is 4 days. So you wash them out easily, but you cannot wash out the hydrogen-trophic methanogens. So what happens is that your practical lever here is pH inhibition. But there's another caveat with this, which is pH limits in any process simulator. So if you look at the pH limits of methanogens of any kind of microorganism in any activated sludge models or any process simulator, you'll see that it ranges from 9.5 to 4.5, which is far beyond what methanogens can tolerate, let alone any kind of bacteria. So they won't get suppressed at all. So upper and lower limits need to be adjusted with anaerobic digestion. Any pH below 6.6, the growth rate tends to be very low. And also beyond 8.5, you end up with free ammonia inhibition. So once you adjust these parameters, you can easily inhibit methanogens in the process. Back to fermentation again, you'll see that in any process simulator, you have something called the fermentation rate, which is the fermentative growth rate of OHOs, which dictates how much VFAs are produced from your fermentable substrate. And these default values are very exaggerated in these models. So you'll see that hydrogen yield is in a high VFA concentration. They basically split fermentation into 2 different scenarios. So one with high VFA production, one with low VFA production. And you'll see that the default values are around 0.35 and 0.1. But in practice, it's actually very low. So it's orders of magnitudes lower. So you would end up producing more hydrogen than you actually are. So these values need to be adjusted. Also, goes back to my first point where hydrolysis might need to be exaggerated sometimes, might not need to be. So default is 3 in one of the a project that I was working on. It had to be increased to 3.3, and in some other case it has to be decreased to 2.8. So it all depends on your setup basically. But fermentation growth rate is also over exaggerated here. So 0.3 and 0.3, those two have to be reduced to 0.05 and 0.04. Normally, you don't have to worry about this if you're not modeling fermentation, because then methanogenesis becomes the rate limiting step. But if you are, then you need to fix all of these. And basically, what if I do none of this? So this is just an exercise here. So you have the influent, and it's split into 2 primary clarifiers, and you have 2 fermenters, one operating at an HRT of 1.4 days and one operating at an HRT of 2.2 days. But you see the gas production over here. You have 53% methane, 47% methane, and 51% hydrogen, 46% hydrogen. All of that at 1.4 days and 2.2 days. And also you have 64% VS reduction and pH of 4.6 and 4.5, which is almost impossible. If you've done that, then congratulations. First of all, you've rendered every pretreatment technology in the past century useless. And also you should be sitting next to your phone, waiting for a call from Stockholm, not listening to me, to be honest, at this point. This is basically what the world would look like if those default kinetics were true. So the take-home message here is that defaults are a starting point, not an answer. Kinetics and stoichiometry are contextual, depending on your substrate and depending on what your goal is. Without proper process understanding, calibration becomes a very tedious trial and error process. And if you fix something and it works, the model also doesn't generalize well. And the burden of calibration is on the user. You can't just use the model as it is with its defaults. there has to be a calibration process regardless of what you're doing. And thank you very much.
Thank you very much, Damien and Amr, for the presentations. We have now some time for a question. So if you have a question, you can just talk through your microphone, or you can also put them in the chat.
If I could, I had a question for Professor Batstone. First of all, thank you both for your amazing presentations. My name is Soroush Sami, doctoral student at University of Technology of Compiègne. So my question was about the 2 points that you said about the disintegration step. So you basically said that you would just plug the different polymers inside your model instead of having a fraction which disintegrates into all of these different fractions. I was curious if that's only out of kinetic considerations or there are other reasons behind that as well. And I had another question, I would just plug that in there as well, which is what would happen if you have like high concentrations of inorganic nitrogen? Because you would take the elemental composition of your feedstock and then just decide protein equals nitrogen balance closure. But if you have a high quantity of NH4, for example, inside your feedstock, would that impact your calculations considerably or not?
Okay, so thanks, Soroush. Great questions and good to see you again. So there's many reasons why we don't use XC. One is the ability to vary our energy density and degradability of different feeds. So if you've just got XC, then every time you change your primary WAS mixture, you have to change your XC composition. And that's kind of ridiculous because you want your X. So if we're trying to say XC represents both primary and WAS, and we increase the primary feed one day, then we'd have to change the composition of XC. Whereas if we've got primary and WAS as separate feeds that are individually fractionated to carbohydrates, proteins, and lipids, then that works out much more easily because we can just change the ratio of the two. So if you've got a high inorganic nitrogen, you just simulate it as high inorganic nitrogen. You just increase the ammonia. And normally, when I mean nitrogen fraction, it's really the organic nitrogen fraction. It has to then be split between XI, which has a very stable nitrogen component to it, and proteins, which has also got a higher stable nitrogen content to it. So yeah, if we've got, and for example, we've got manure, then manure will have a lot of inorganic nitrogen in it and a relatively small amount of organic nitrogen. So manure's actually got a high nitrogen content, but a very low protein content because it's all the nitrogen is as inorganic nitrogen, as ammonia.
Thank you.
Is there any other questions?
Hello? Can I ask something? Okay. Hi, Damien. How are you?
Hi, good, thanks.
So congrats for the presentation. We're really good, really like cut to the chase, straight to the point. So kudos for both of you. Can you elaborate a little bit more in regards to how to distinguish between carbohydrates and protein from the substrate? You talk about some energy density, something like that, I think I didn't get quite right. So
yeah, so to take an example, so let's say we've got activated sludge, which has got a nitrogen content or a nitrogen ratio of 0.007 moles per kilogram CAD. I know that's, I might just type some of this in the chat. So WAS nitrogen content of 0.007 moles N per gram CAD. So to then, if we then want to match, So we know that amino acids or protein has got a nitrogen content of about 0.012 mole N per gram COD. So we then have to have enough protein that we basically represent all of that 0.007, which means that we normally need a protein content of about 0.3 to 0.4. Okay, so that then sets our protein content, right? But then we also know that the COD/VS ratio is, let's say, 1.9. And to get that COD ratio, because carbohydrates have a COD/VS of 1, fats have a COD/VS of 2.5. So to get that net COD/VS ratio of 1.9, we need to have around 40% fats and 20% carbs. Yeah.
Then by difference, you get the lipids. By difference, you get the lipids.
That's right. Yeah. So by difference, we get the lipids. The convenient thing is that inerts have about a nitrogen content of 0.007 as well. So that's how it basically gets fractionated with 2 or 3 degrees of freezing. And we have to fulfill those. Yep.
Thanks.
I've got an Excel spreadsheet that I should post at some point.
I appreciate that.
Is there any other questions?
So if I may ask, maybe just something else.
Sure.
So if I understood what you just both presented, you would say that the ADM1 is very versatile. It can be used for different processes, different substrate, different conditions. So there isn't really a need to come up with a new version of the ADM1. Is that right?
I think there's so the feedback I've had from particularly Imre Takac from Sumo said this. He said there's too many versions and there's no consolidation. So any people coming to modeling new, they don't know which version they should use. Should they use? I think there was something like 15 or 20 different versions of Aquasim, because a lot of people have created it brand new, but also a lot of people have used the version that I shared when we first wrote the model. There's at least 3 versions of Python. There's probably 2 or 3 versions of MATLAB or MATLAB C. So there's a lot of confusion around that. I think that's maybe something we should do, is just produce a consolidated version and call that ADM2 if you want. But it's hard to say, okay, we need to always have acetate oxidation, because you don't. It's very rare that you actually need acetate oxidation. It's not like the difference between the ASM2D and ASM1, where there was a clear difference there that really justified publication of ASM2D. Got a bit of background noise from Santa. Yeah, I'm not sure. A lot of people still are asking, should we do an ADM2? I've always said, yeah, we need, but I think now maybe at least a publication that says here's a definitive version and here's how you use it might be useful. But it won't be me, because I'm at a different stage of my career now. So if anybody wants to step up, then maybe that's a good thing to do.
Mm-hmm. Maybe with a version for MATLAB, C++, and Python, like a consolidated package for people to use.
All the same, all completely verified. Yeah, that'd be great.
Yeah.
If I could squeeze in one last question about exactly the comparison of ADM1 with like more simplified models. One simplification that I tend to see almost every time is the representation of all volatile fatty acids by acetate. I wanted to know what your thoughts were on this simplification in particular, and in which cases would it, in which, let's say, type of processes or substrates would that be an illegitimate choice of simplification?
Yeah, if you're operating under circumstances where you never really overload the digester to the point where you get propionate appearing, I think that is certainly fair. If your failure mode is mainly related to ammonia inhibition and you never get substantial, in a way you're representing, or it's not just acetate, it could be all the BFAs, and that's kind of tricky because you really need the change in COD mass ratio. It doesn't represent. I'd say if you're mainly challenged by I guess performance, so hydrolysis rather than stability, but you want to also represent what happens when the BFAs accumulate, I think you need that's when you could use that model. I'm not really an expert. I either use really simple, so just first order, or ADM1. So I don't tend to use the BFA models. Even Sumo and Biowind have found it necessary to include propionate. I think that says something about the minimum number of BFAs you need, because propionate does behave so differently from acetate. I would say, yeah, that for me, it's either first order, single step, or much more complex ADM1, other basic ones you go to. Not that I wouldn't say that the acetate only one or the acetate plus propionate ones are not also useful. It's just been my experience.
Thank you.
It depends on the goal that you're trying to achieve, basically. So you don't care about the intermediates if your goal is anaerobic digestion and methane production at the end of the day. You can simplify the middle steps as much as possible. You'll still get your methane because it's just COD removal versus the stoichiometric conversion. But if your goal is VFA fractionation and you're doing fermentation, then there's a lot of thermodynamic models that actually do that. But it's also you also get into a different realm of assumptions and model complexity. So it all depends on what you want to do with it.
There's been a very nice systematic analysis by Soren Weinrich with a number of standardized simplifications being provided that actually is being more broadly used now as well. So I'll just put that in the chat as well. And that's being used a lot in commercial digester modeling in Europe. But yeah, absolutely, I agree with that as well.
So to pin that point, so he simplifies the model in 4 consecutive steps. So which step would you say would still be representative of the process? Because the 4th one is, as you said, just the first order model. In the end, which step would contain like the least number of steps while still being representative of the different cases of inhibition which could occur?
I don't know, and I have to just accept the fact that people use all 4 under different circumstances, because as I say, I use number 1 and number 4, and I haven't really played with the other ones. So I accept, given the fact that different ones are being used, that they're all basically valid. If they're used, then they're useful.
Okay, thank you.
Any other question? Okay, so if there's no more questions, I would like to thank the speakers of today very much for your presentations. This session will be uploaded to YouTube probably by the end of the week. Okay, so thank you everyone for joining, and hope to see you in the next session.
Thank you.
Thank you to you and Amir, particularly for producing a presentation and for inviting me. I really appreciate it, and I appreciate the effort that you went to, Amir, in preparing and giving a unique perspective as well. So thank you very much.
Thank you.